Look up at the night sky. What do you see? Groups of stars, distant galaxies, and mysteries waiting to be solved. But how do we begin to understand the universe? It all starts with the concept of relativity. The story of relativity begins in 1632, when the Italian physicist, mathematician, and astronomer Galileo Galilei articulated a fundamental principle in his seminal work, Dialogue Concerning the Two Chief World Systems. This principle states that it is impossible by mechanical means to determine whether we are moving or staying at rest. Simply put, the laws governing motion and mechanics are identical in all constant velocity reference frames. This laid the groundwork for what would eventually become the theory of relativity. Galileo's motivation for this principle was to defend the Copernican heliocentric model of the universe, which posited that the Earth revolves around the Sun, contrary to the prevailing geocentric model that placed Earth at the center with all celestial bodies revolving around it. Skeptics of Copernicus's theory argued that if the Earth were indeed in motion, we would be able to feel this motion. To counter these skeptics, Galileo provided a thought experiment. To illustrate his point, Galileo devised a thought experiment that remains one of the clearest demonstrations of the principle of relativity. He asked us to imagine ourselves inside the main cabin below decks on a large, smoothly sailing ship. In this closed environment, Galileo described a series of observations involving various small animals and objects. Imagine you have some flies, butterflies, and other small flying animals within the cabin. A large bowl of water containing fish is also present. A bottle is hung up that empties drop by drop into a wide vessel beneath it. You throw an object at a friend within the cabin, and you jump with your feet together. As the ship remains stationary, these animals fly with equal speed in all directions. They do not show any preference or change in their flight patterns. The fish swim indifferently in all directions, unaffected by any external motion or force. The water drops fall straight down into the vessel without any deviation. The force needed to throw the object remains the same in all directions, indicating no influence from the ship's motion. The distance you jump is the same in every direction. After establishing these observations on a stationary ship, Galileo then asked us to imagine the ship proceeding at any constant speed, ensuring the motion was uniform and not fluctuating. He concluded that all previously observed phenomena would remain unchanged. There would be no detectable difference in the behavior of the animals, the fish, the water drops, the thrown objects, or the jumping movements. Galileo concluded by saying, "You will discover not the least change in all the effects named, nor could you tell from any of them whether the ship was moving or standing still." This thought experiment powerfully demonstrates that within a closed system moving at constant velocity, the laws of physics operate identically as they do in a stationary system. Thus, whether the ship is at rest or in uniform motion, the internal observations remain consistent and indistinguishable. This insight directly challenged the intuitive notion that motion should be felt or detected inherently. Instead, Galileo showed that it is impossible to discern uniform motion from a stationary state through internal observations alone. Galileo's thought experiment served as a rebuttal to these skeptics of Copernicus's theory. This principle, often referred to as Galilean relativity, implies that the laws of physics are the same in all inertial frames of reference. This concept was revolutionary because it suggested that no inertial frame is privileged over another, and there is no absolute state of rest. Galilean relativity implies that there is no absolute frame of reference. Instead, motion is always relative to some other object or frame. This was a significant departure from the Aristotelian view, which held that the Earth was the center of the universe, and all motion was absolute and referenced to it. Galileo's principle paved the way for a more dynamic and less Earth-centric view of the universe. In short, Galileo said motion is relative, and there is no absolute frame of reference. All inertial frames are equivalent to the description of the laws of mechanics. Objects in uniform motion remain in uniform motion unless acted upon by an external force reflecting the principle of inertia. Nearly 55 years later, the English mathematician, physicist, and astronomer Isaac Newton expanded on Galileo's ideas. Newtonian relativity extends Galilean relativity by providing a comprehensive mathematical framework for understanding how forces and motion operate in different inertial frames. Newton introduced the three laws of motion and the law of universal gravitation, which are the cornerstones of classical mechanics. Let's discuss these three laws of motion. The first law, also known as the law of inertia, states that an object at rest stays at rest, and an object in motion stays in motion with the same speed and in the same direction unless acted upon by a net external force. This means that in the absence of a net external force, an object will maintain its current state of motion. This concept of inertia builds on Galileo's observations and implies that motion, or lack thereof, does not require a cause. The second law, also known as the law of acceleration, states that the acceleration of an object is directly proportional to the net force acting on it and inversely proportional to its mass. This is mathematically expressed as F equals ma, where F is the net force, m is the mass, and a is the acceleration. It implies that the same force will produce different accelerations depending on the mass of the object and establishes a direct proportionality between force and acceleration. The third law, also known as the law of action and reaction, states that for every action there is an equal and opposite reaction. This means that forces always occur in pairs. If object A exerts a force on object B exerts an equal and opposite force on object A. This principle is essential for understanding interactions between objects. These three laws apply universally and are invariant in all inertial frames of reference, reinforcing the principle of relativity. Newton also proposed the law of universal gravitation, which states that every point mass attracts every other point mass with a force that is directly proportional to the product of their masses and inversely proportional to the square of the distance between them. The formula is F equals gm1 m2 by r squared, where F is the gravitational force, g is the gravitational constant, m1 and m2 are the masses, and r is the distance between their centers. Newtonian mechanics, also known as classical mechanics, describes the motion of objects based on his three laws of motion and the law of universal gravitation. While Galilean relativity implies that the laws of physics are the same in all inertial frames, it does not address the nature of space and time. Newton introduced the concepts of absolute space and absolute time. According to Newton, space is a fixed, unchanging framework within which objects exist and move. It provides a backdrop against which motion can be measured and exists independently of any objects within it. Newton stated, absolute space, in its own nature, without regard to anything external, remains always similar and immovable. Time, according to Newton, flows uniformly and independently of any external influences. It provides a universal clock for all observers. Newton said, absolute, true, and mathematical time of itself and from its own nature flows equably without relation to anything external. These concepts allowed Newton to define motion in a clear and unambiguous manner, establishing a consistent framework for classical mechanics. Newton once said that his insights and breakthroughs were made possible because he built upon the foundational work of others. In a letter to Robert Hooke in 1676, he wrote, "If I have seen further, it is by standing on the shoulders of giants." In short, Newton said space and time are absolute along with three laws of motion and the law of gravitation. To illustrate the principles of Galilean and Newtonian relativity in real life, let's dive into a classic analogy involving a train and an observer. Imagine your friend Alex is inside a train moving at a constant speed of 50 kilometers per hour. For Alex, the world outside the train is a blur of passing trees and fleeting stations. Meanwhile, you stand outside, notebook in hand, measuring the train's velocity. From your frame of reference, it's indeed moving along at 50 kilometers per hour. Now, let's add another layer to this scenario. Suppose another train, moving at 45 kilometers per hour, is approaching Alex's train on a parallel track. For the people inside the second train, Alex's train appears to be moving at only 5 kilometers per hour. Here's the question. Is the actual speed of Alex's train 50 kilometers per hour from your perspective, or 5 kilometers per hour from the perspective of the second train's passengers? The answer is that both measurements are correct from their respective frames of reference. This example demonstrates that motion is relative. The speed of Alex's train is not an absolute value, but depends on the observer's frame of reference. This is a key idea in both Galilean and Newtonian relativity. The laws of motion are the same in all inertial, that is, non-accelerating frames of reference. There is no absolute frame of reference. Motion can only be described relative to another object. In our train scenario, whether you are on the platform or on the approaching train, the laws of motion remain consistent. This means that all inertial observers like you, Alex, and the passengers on the second train will observe the same physical laws, even though they might measure different velocities. The fundamental laws of physics, including Newton's laws of motion, apply universally in all inertial frames. There is no preferred inertial frame of reference, and all inertial observers are equally valid in describing physical phenomena. Another crucial point is that there is no absolute rest. Even if you believe you are standing still on the platform, in reality, you are moving at the speed of the Earth's rotation. The Earth itself is not at rest. It orbits the Sun, which in turn moves around the center of the Milky Way galaxy, and so on. The concepts of absolute space and absolute time allows for a consistent framework to describe motion, even though motion itself is relative. In summary, the relativity of motion and the invariance of physical laws in all inertial frames form the foundation of both Galilean and Newtonian relativity. Understanding these principles helps us appreciate the dynamic nature of our universe and the interconnectedness of all motion. Imagine you're having a conversation with a friend inside the cabin of Galileo's ship. Whether the ship is at rest or moving at a constant speed, the propagation of sound waves remains consistent. These sound waves, produced by vibrating objects such as your vocal cords, travel through the air by compressing and rarefying air particles. The speed of sound waves depends on properties like air density and temperature, rather than the ship's motion. Consequently, conversations occur normally inside the cabin because the air moves with the same velocity as the passengers. A similar phenomenon occurs with water waves. However, things change when we move to the deck of Galileo's ship and observe the sound waves from another boat's horn. The perceived speed of these waves changes based on our motion relative to the medium propagating the waves. This phenomenon can be explained by the principles of relative motion. Imagine you are standing still in the ocean as waves come toward you at 10 kilometers per hour. If you remain stationary, the water waves will hit you at their natural speed of 10 kilometers per hour. But if you jump on a jet ski and head directly into the waves at 40 kilometers per hour, the relative speed of the waves increases. The waves appear to move toward you at 50 kilometers per hour. Conversely, if you move away from the waves, the relative speed becomes negative 30 kilometers per hour. In the same way, sound waves from a distant boat horn travel through still air at 1,240 kilometers per hour toward the shore. If you move toward the sound source on a jet ski at 60 kilometers per hour, the relative speed of the sound waves increases to 1,300 kilometers per hour. This change in the perceived speed of waves due to relative motion is closely related to the Doppler effect, a phenomenon observed in all types of waves, including light. First described in 1842 by the Austrian physicist Christian Doppler, the Doppler effect explains the change in frequency and wavelength of a wave in relation to an observer moving relative to the wave source. As you move toward a sound source, the sound waves compress, leading to a higher frequency and pitch. As you move away from the sound source, the sound waves stretch, leading to a lower frequency and pitch. This is why, as a car approaches, its siren sounds higher pitched, and as it moves away, the pitch drops. The Doppler effect is also used in cosmology to determine the movement of stars and galaxies by observing the shift in the frequency of light they emit. Does light behave the same way as sound and water waves do? Physicists of that time wanted to know the answer to this question. However, this question has its roots in scientific debates that stretch back centuries. Some suggested light is particle in nature, while others suggested light has wave nature. In the 1600s, Isaac Newton proposed a bold idea about light. He envisioned it as a stream of tiny particles, or corpuscles, that traveled in straight lines. According to Newton's particle theory, these light particles moved like miniature billiard balls, bouncing off surfaces to explain reflection and bending slightly when entering different mediums to explain refraction. Newton's immense influence and the straightforward nature of his theory made it widely accepted during his time. Contemporaneously to Newton, Christian Huygens proposed an alternative theory. He suggested that light should be understood as a wave, similar to ripples spreading across a pond. According to Huygens' wave theory, light waves create disturbances in a medium, propagating outward in all directions. This idea was revolutionary because it could explain phenomena that Newton's particle theory struggled with, such as diffraction and interference, effects observed when light bends around obstacles or passes through narrow slits. Now we know that light behaves both as a wave and a particle, a concept known as wave-particle duality. This duality is a cornerstone of quantum mechanics and helps explain how light can exhibit characteristics of both particles and waves. By the late 19th century, numerous experiments had provided strong evidence supporting the wave theory of light. Thomas Young conducted a famous experiment in 1801 where he passed light through two closely spaced slits and observed the resulting pattern on a screen. Young observed an interference pattern characterized by a series of bright and dark fringes. This pattern was analogous to the interference patterns created by water waves passing through two slits. The interference pattern could be explained by the wave nature of light. The crests and troughs of the waves emanating from each slit reinforced each other in some places, creating constructive interference, and canceled each other out in other places, creating destructive interference. In the mid-19th century, the Scottish physicist James Clerk Maxwell further enshrined the wave theory of light. He developed a set of equations that describe the behavior of electric and magnetic fields. Maxwell theorized that these fields could propagate through space as waves. Maxwell's equations predicted the existence of electromagnetic waves, which included light as a form of these waves. Maxwell calculated that these electromagnetic waves would travel at a speed of approximately 299,792,458 meters per second, which coincided with the measured speed of light. This was a critical piece of evidence linking light to electromagnetic waves. Maxwell's theory led to a deeper understanding of the electromagnetic spectrum, which includes a wide range of wavelengths and frequencies beyond visible light. With wavelengths around 300 yards, AM radio waves are at the longer end of the electromagnetic spectrum. FM radio waves have shorter wavelengths of approximately 3 yards. Microwaves have even shorter wavelengths around 3 inches and are commonly used in communication technology and microwave ovens. The visible spectrum ranges from red light with wavelengths of about 25 millionths of an inch to violet light with wavelengths of about 14 millionths of an inch. As the wavelength of light decreases, the frequency increases, resulting in different colors visible to the human eye. UV rays have wavelengths shorter than visible light and can cause chemical reactions such as those leading to sunburn. X-rays have even shorter wavelengths and are capable of penetrating many materials, making them useful for medical imaging. Gamma rays possess the shortest wavelengths and highest frequencies, and they are highly energetic, often produced by radioactive decay and astrophysical processes. Thus, when the wavelength increases, the frequency decreases, leading to lower energy. Conversely, shorter wavelengths have higher frequencies and greater energy. James Clerk Maxwell theorized that the speed of light and all electromagnetic waves is 299,792,458 meters per second. But this notion raised two big questions. The first question is, what is the medium that propagates these waves? And the second question is, this speed of 299,792,458 meters per second is a speed relative to what? In the case of sound waves, air is responsible for the transfer of sound. So physicists of that era, building on the wave theory of light, proposed the existence of an unseen medium through which light waves traveled. This hypothetical medium was known as luminiferous ether, or simply ether, an idea that became central to the discussions and experiments of the time. This ether was postulated to be an all-pervading, elastic medium that filled the entire universe. It was thought to be necessary for the propagation of light waves in a manner similar to how air carries sound waves. According to this theory, light waves were disturbances or vibrations within this ether, and their speed was relative to it. However, this ether, unfortunately, had many puzzling properties. Since light from distant stars reaches the Earth, the ether had to pervade the entire known universe. Also, the ether needed to be so delicate and insubstantial that it had no discernible effect on physical objects like planets or feathers floating through it. Despite its gossamer nature, the ether had to be stiff enough to support the rapid vibrations of light waves, which travel at speeds of approximately 299,792,458 meters per second. Due to these properties, some scientists assumed that the ether was stationary and that the Earth moved through it freely. If this were the case, light waves should appear to travel faster when moving through the ether toward a light source, while others posited that the Earth might drag some of the ether along with it, similar to how it carries its own atmosphere. This would imply that measurements of light speed might vary depending on the relative motion of the Earth and the ether. A more radical and unlikely idea was that the Earth was the only object at rest relative to the ether, and everything else in the cosmos, including the other planets, the sun, and the stars, was in motion. This was a last-ditch attempt to reconcile observations with the ether theory. By the late 19th and early 20th centuries, the Great Ether Hunt became a significant scientific inquiry into the nature of light and the hypothetical medium known as the ether. Two landmark experiments, conducted by Hippolyte Fizeau and the duo of Albert Michelson and Edward Morley, played crucial roles in shaping the understanding of light propagation and eventually led to the downfall of the ether theory. Hippolyte Fizeau, a French physicist, conducted a groundbreaking experiment in 1851 to measure the speed of light in a moving medium. This experiment was later deemed one of fundamental importance in the special theory of relativity by Einstein. Fizeau's goal was to determine how the speed of light is affected by the motion of the medium through which it travels. Fizeau used a half-silvered angled mirror to split a light beam into two parts. One part of the beam was directed through water flowing in the same direction as the light, while the other part was directed against the flow of water. After passing through their respective paths, the two parts of the light beam were reunited. The experimenters analyzed the resulting interference pattern to determine if one route took longer than the other. If the light beam traveling with the water's flow moved faster, the crests and troughs of its waves would be out of sync with those of the beam traveling against the flow. This would create a detectable shift in the interference pattern. According to prevailing theories, light traveling through a moving medium would be dragged along by the medium. Thus, the measured speed of light should be the sum of its speed through the medium and the medium's speed. Fizeau indeed detected a dragging effect, but its magnitude was lower than expected. When he repeated the experiment with air instead of water, he observed no effect. Fizeau's experiment provided crucial data on the relationship between light speed and the motion of the medium. In 1887, in Cleveland, Ohio, Albert A. Michelson and Edward W. Morley conducted one of the most famous experiments in the history of physics, known as the Michelson-Morley experiment. The goal was to detect the relative motion of matter through the stationary ether, often referred to as ether wind, by comparing the speed of light in perpendicular directions. Michelson and Morley built an interferometer that splits a light beam into two parts. One part traveled back and forth along an arm aligned with the direction of the Earth's movement, while the other part traveled along an arm at a 90-degree angle to it. When the two parts of the beam were rejoined, the resulting interference pattern was analyzed to see if the path aligned with the supposed ether wind took longer. If the ether existed and the Earth moved through it, the light beam traveling against the ether wind would take longer, resulting in a shift in the interference pattern. However, This experiment consistently failed to detect any significant difference in the speed of light along the two paths. This null result indicated that the speed of light was constant regardless of the Earth's motion through space, challenging the existence of the ether. The Michelson-Morley experiment was a major blow to the ether hypothesis, suggesting either the ether did not exist or the understanding of light propagation needed a fundamental revision. Based on the Michelson-Morley experiment in the early 1890s, Dutch physicist Hendrik Lorentz and independently Irish physicist George Fitzgerald proposed a theory. They suggested that objects contract in length when they move through the ether. This contraction, known as the Lorentz-Fitzgerald contraction, was theorized to be exactly the amount needed to nullify the expected effects of the ether on light. This hypothesis suggests that the measuring arms of the Michelson-Morley interferometer contracted just enough to cancel out any differences in light speed caused by the ether wind, making the ether undetectable. Einstein found the prevailing situation very depressing. He noted that scientists were unable to explain electromagnetism using the Newtonian mechanical view of nature, leading to a fundamental and unsustainable dualism in physics. This prompted him to develop his revolutionary theory of special relativity, which eventually resolved the paradoxes and inconsistencies surrounding the nature of light and motion. However, this new theory provided a unified framework for understanding the constancy of the speed of light and the relativity of space and time, marking a significant milestone in the history of physics. This is what Einstein exactly did in 1905. He introduced his special theory of relativity, which eliminated the need for the ether. In the next video, we will discuss it in detail. From the lessons learned and the progress achieved through persistent scientific inquiry, we know that the smallest details pave the way for the greatest discoveries. As Alexander Graham Bell once said, "Great discoveries and improvements invariably involve the cooperation of many minds."